Hello everybody, I hope you're all doing well. We're going to be solving one more problem on motion relative to rotating axes. Okay, so in this problem I have a disk that is rolling without slip relative to the ground. Okay, so I'm given the following information. Okay, so disk rolls without slip relative to the fixed ground. Okay, and we are also shown that there is a peg at the point A on this particular disk. Okay, this is embedded in the disk. Okay, so there's a peg or a pin if you want to think of it. Okay, pin A is embedded in the disk, which implies that the point A and point O, which is the center of the disk, they are points on the same rigid body. Okay, so points peg A and point O are points on the same body. Okay. Then what else are we told? We are told that the angular velocity of the disk is 20 radians per second, that is given to you here, and the angular acceleration of the disk is 5 radians per second. We are told that one of them is clockwise, the other is counterclockwise, so be careful. Okay, so that's shown here. And we are told that at that instant in time, as you're seeing it, at that instant in time, the angle between the peg at A and point O with respect to the horizontal is 60 degrees. Okay, and the peg A is approximately at the end of the disk, so we can assume it to be at the edge or the circumference of the disk. Okay, so let me write that down here. So the peg A is at the circumference of the disk, which implies that the distance from the peg A to O is the same as the radius of the disk. Okay, so this is an approximation that we are making. The problem is also telling us about this. Okay, and to begin with, then I have a bar BC with a slot cut into it. Okay, and this bar BC is pinned at the point B, and the peg is sliding within this slot, as you can see. Okay, so bar BC has a slot cut into it, has a slot cut in it, and the peg A can slide within this slot. Okay, so the peg A will slide within this slot. Okay, so this is the information that is given to me, and I'm told the distance from point A to point B is 0.53 meters, and to a great approximation we can say that point B and point O are along the same straight horizontal line. Okay, so point B and point O are at the same elevation. Let's make a note of that as well. So note B and O are at the same elevation from the fixed ground. Alright, beautiful. So what do we need to do in this problem? Since I'm given the angular velocity of the disk and the angular acceleration of the disk, it is quite obvious that I need to find the angular velocity and acceleration of the bar BC. So that's the first thing I need to do. Okay, so obtain. So this is given here, and we need to obtain the following. Let me also write down and say that this is information that is given to us. Okay, so given. And as you read the problem, you'll realize that a lot of the information that is given to us is what is going to help us solve the problem. Okay, so what do we need to obtain? First thing is the angular velocity and angular acceleration of the bar BC. Okay, and the second thing, let us find the velocity and acceleration of A relative to the bar BC. Okay, so obtain the velocity of the peg A relative to the bar BC, and the third thing is we'll obtain the acceleration of peg A of peg A relative to bar BC. All right, and we should also note that the peg A is not a part of the bar BC. Okay, so also note here that the peg A is not a part of bar BC, it is a part of the disk. Okay, is a part of the disk. Okay, so that's something that we have already maybe probably noted down earlier, but I just want to note it again. Alright, so fantastic. Here is the problem. I have a disk, rolls without slip with respect to the flat horizontal fixed ground. Okay, and there is a peg A which is embedded in the disk, and this is at a distance of 0.2 meters from the center, makes an angle of 60 degrees with respect to the horizontal. We are told that this is approximately at the circumference of the disk, which means that the radius of the disk is the same as the distance from point A to point O. Okay, then I'm told that at that instant in time, so this is a figure that is given at that instant in time. Okay, so let me also make a note of that. Okay, so this figure is at that instant in time, so figure is at that instant in time. Okay, so that's essentially what it is. Then I have a bar BC with a slot cut into it, and we are told that the peg moves relative to the bar BC. So I need to find the angular velocity of the bar BC, need to find its angular acceleration as well as the relative velocity and acceleration of A with respect to the bar BC. Okay, so these are the things we need to find out. I'm going to grab this figure, and we will start analyzing it one by one. Okay, so I'm going to copy this, hopefully nothing changed. All right, and then I'll come and bring it here. So my solution. Okay, so I'll paste my figure here so that it's looking at it this way. Let me get rid of that. Alright, so how do I solve this problem? I realize that A is a part of the disk, so I'm going to analyze just the disk. Okay, so that's my first strategy. So A is a part of the disk, which means analyze the disk only first. Okay, then we can bring together, so this will enable us to find the velocity and acceleration of A. Okay, so this means that we can try to find the absolute velocity of A, the absolute acceleration of A. Okay, so these are the absolute velocity and acceleration. That's something that you want to specify. Okay, so these are the absolute velocity and acceleration. Then once I find this, I go back to the bar BC, and then I make use of relative motion equations and try to combine everything together. Okay, so then go to bar BC, make use of relative motion equations. Okay, and this will help combine everything together. About peg A and bar BC. Okay, so this is my strategy. And something that you can see obviously in this problem is that the distance between point O and A remains fixed. Distance between point A and B is not fixed. Okay, as you can see, because A is not a part of the bar BC. Okay, so let's write this down. Let me just take the disk only. and hopefully I'm able to capture everything that comes along with it. Let's see. Okay, so I'm going to copy all of this. I'm just going to analyze only the disk. Okay, and I'm going to put this up here. So I missed out on getting the peg, but I can probably copy that piece as well. So I'm going to copy that, and I'm going to bring that down here. Okay, so here is a peg which is approximately at the end of the disk, so if you want to think of it that way. All right, so now I'm going to set up a coordinate frame and so on. So I know the direction of omega d and alpha d, which is d for the disk. Okay, so I know, let's call the point of contact. So this is point A here. Okay, let me call the point of contact with the ground as the point C, and let me just draw a straight line connecting the two. So this point I'm going to call as the point C, and then this is G, which is on the ground, and then I set up a coordinate frame here. Okay, so as you know, this is going to be a tangential coordinate frame, which is tangent to the contact between the ground and the point C. Okay, that looks approximately tangential. Okay, so I'm going to call it as T, and then I'm going to have a normal coordinate direction, which is going to be N, which is pointing this way. Okay, then outside the frame of the problem, I'm going to have the IJK coordinate frame. Okay, so this is J, I, and K. K coming out of the page. So I, J, and K. Okay, and the important thing is, okay, we are looking at the disk first. That is true. And what I want to see is these are all points on the same disk. So points A, O, and C. All points on the same rigid body. Okay, so that's important. Then I make use of the idea of rolling without slip, which means that at the point of contact, I'm going to have a zero relative velocity. So velocity of C relative to G is equal to 0, which means that velocity of C is equal to velocity of G, and this is both equal to 0, right? We'll write this separately. Okay, so that's there, but G is fixed, which means that velocity of G is equal to 0. So this tells me that velocity of point C is 0. Okay, 0 vector. And that's the first condition of rolling without slip. The second condition of rolling without slip is that the relative acceleration in the tangential direction is 0, which tells me that acceleration of C in the tangential direction is equal to acceleration of G in the tangential direction, but G is fixed, which implies that its acceleration in the tangential direction is 0, which tells me that the acceleration of C in the tangential direction is 0. I'm just going to make a little more space for this so that I can squeeze all of this on to this single page here. Okay, so please bear with me while I push up stuff. Alright, that is fantastic. Okay, so this essentially tells me that acceleration of C in the tangential direction is 0, which tells me that acceleration of C, the total acceleration of C, is going to have a 0 component in the tangential direction. The tangential direction is coincident with I, so that's also something you can write. So at that instant, okay, the tangential direction is coincident with the direction I, and the normal direction is coincident with the with the direction J. This is at that instant, so I can say that this is 0 in the I direction and something in the J direction. Okay. Alright, so those are the two things that we have obtained from the idea of rolling without slip. Okay. Alright, fantastic. Then what do? I can find the velocity of point O using this and using the omega as well, or I could directly find the velocity of A. There are two options that I have here. Okay, it doesn't matter really as to what the options are. I can make use of it in the following manner, but let me find the velocity of O and then the acceleration of O first. Okay, so velocity of O is velocity of C omega of the disk crossed with r from C to O, and then this V relative. Okay, so this is O slash C relative, which is gone, okay, because they are on the same disk. VC is also gone, okay, so which implies that V naught is omega of the disk, which is in the K direction. So that's something that we could have written down here. Okay, so omega of the disk is minus 20K radians per second. Alpha of the disk is given to us as 5K radians per second square. Okay, this is based purely on the figure. Okay, so if that is the case, this is going to be minus 20K crossed with the position vector from point O to point C, which is the radius. I'll just draw it out here. Okay, this is point O, this is point C, this is the position vector from C to O. This is nothing but the radius r in the j direction. Okay, so this is going to be r in the j direction, and this is the distance r, as you can see. Okay, and r I think was given to us as 0.2 meters, so let me write this as 0.2 j, so many meters, and let me do the substitution here. Okay, so 0.2. all right, so this tells me that the velocity of point O is going to be 4 I meters per second. Okay, so that's that. Then using this, I'm going to find the velocity of point A. Okay, so that's another thing that I'm going to be doing. So relate the velocity of A to velocity of O, because my aim is to find the velocity of A and acceleration of A with respect to an absolute observer, and make use of that when I go to the bar BC. Okay, so that is my strategy here. All right, so velocity of A is velocity of O, omega of the disk crossed with r A slash O, and then I'm going to have V of A slash O relative. That relative term is gone. Or A slash O. How do I do that? So I draw a very quick figure here. Okay, so point A and then point O. Those are the 2 points here. So this is A, this is O, and this vector here is R, A slash O, and I know the angle is 60 degrees with respect to the horizontal. So this angle is given to me as 60 degrees. So this is going to be 0.2 cosine 60 and 0.2 sine 60. Okay, so I can write out R A slash O as the following. So velocity of A is 4I, and then omega of the disk is minus 20K crossed with 0.2 negative cosine 60 in the I, and then plus 0.2 sine 60 J. Okay, because I'm traveling to the left and then I'm traveling up in order to find the location of point A from point O. So traveling left means minus I, traveling right, traveling up means positive J. Alright, do the substitutions. I have the numbers crunched out here. So velocity of A will end up being the following. Okay, it's going to be k cross I is j, k cross j is minus I, and so on. We know how to do the triads now. So this is 7.46 in the I direction, and then 2 in the j direction. So many meters per second. Alright, so that's one thing done. Then acceleration analysis. Okay, so this is all velocity analysis for points O and point A. I do the same thing for the acceleration analysis. Now acceleration of O is going to be only in the I direction, right? Why is that? If I go back here, the acceleration of O cannot be in the J direction, because then the disk will lift off of the ground, which is violating the problem conditions. Okay, so this is because we do not want the disk to lift off the ground. Okay, so which is why its J component is 0. Okay, then I also know that acceleration of C is 0I and then something in the J direction. This is coming from the roll without slip. Okay, and I know the position vector as well between the two. are from O to C, which we had written down as 0.2j, so many meters, and we had alpha of the disk given to us as 5k radians per second square. Omega of the disk was 20 radians per second, the magnitude. Okay, so using all of these quantities, I'm just going to write the acceleration of O. Acceleration of O is going to be acceleration of C, alpha of the disk cross r from C to O, omega square of the disk times r from C to O, then this relative term, and then this other term, omega of the disk crossed with V OC relative. Okay, so in this I can cancel off these relative terms because we are sitting on the same body. Okay, then I just do the substitutions. A0 is A0 in the I direction, AC is 0I, and then ACN in the J direction. Alpha of the disk is going to be 5k crossed with 0.2j minus 20 square times 0.2j. Okay, that's going to be the 0.2j is RO/C. Alright, so if I now take the I terms, I get the following. A0 is going to be 0I, then k cross j is minus I, right? And so I will be able to obtain the acceleration as minus 1I meters per second square. Okay, and if I take the j terms, I can of course obtain 0 is equal to ACN minus 20 times 0.2, which implies that ACN is 400 times 0.2 or 80 meters per second square. Okay, it's not necessary for us. Now some of you may have asked, why am I not relating acceleration of A to acceleration of C directly? Why did we not relate acceleration of A to acceleration of C directly? And the answer is because I don't know the acceleration of C completely, and it is possible that the acceleration of A can have a component in the J and the I directions. Okay, so the reason is we did not know AC, which was 0I, AC and J to begin with, and acceleration of A could have a component in the I and the J direction. Okay, so then if I try to find the J component of acceleration of A, then I wouldn't be able to do that because I don't know the acceleration of C in the J direction, right? So this normal component is not known to me. So which is why I would not have been able to relate AA to AC directly. I have to find A0 and then find AA. So which is why, so we need to find A0 or AC and then find acceleration of A. I hope this makes sense. Okay, this is a key statement here. Why am I doing certain things? Why am I not doing certain things? Okay. All right. So now I think we are ready to look at the acceleration of point A. So let me go ahead and do that. So acceleration of A, I have two choices. I can either do the following. I could either do, this is acceleration of O, alpha of the disk crossed with R, A/O, omega square of the disk times R A/O, and then all these relative terms will cancel off, as you know, at least for this particular part of the problem. Okay, so that term is gone, that term is gone. Or I could also do, since we now know acceleration of C, could also do acceleration of A is acceleration of C, and all the rest of the terms, quite painful to write, but let me do that. That's acceleration of c there, I'm sorry, relative to c, and then all these relative terms that cancel off. Okay, so I could either use this one or I could use that one. Okay, so let me just call this as A and B. Okay, so can use either A or B. Or B to obtain acceleration of A. Okay, I'm just going to use A. Okay, so use A. Start filling in the details. Okay, I already know RA/O as minus 0.2 cosine 60I and 0.2 sine 60J, so many meters. How did I know that? That is by looking at what we have done earlier. Okay, so that's how I know it. Alright, and then I go ahead and I pull it into the expression. So acceleration of A is acceleration of O, which I found as minus 1I, and then alpha is 5k crossed with that term there, 0.2 negative 0.2 cosine 60I, 0.2 sine 60j minus omega square, which is 20 square, times that entire thing. I'm just gonna copy that and then paste that down here. Well, I'm running into trouble. Hang on. I'm just gonna scoot this over a little more. And I think now I should be good to go. Okay. And we can do k cross I, k cross j, and so on. So I'm just going to skip the details of this one so that I can directly write the acceleration of A. Okay, so after you do the math, acceleration of A will end up being the following. Okay, it's 38.1 I and then minus 70.2 in the j direction. Okay, the negative is coming because I have a 400 times 0.2 sine 60 and then I have another term contributing in the j direction. Okay, so this is so many meters per second square. Alright, so far what we have is the following. So after analyzing the disk, okay, we have the following. Okay, velocity of A is known, the acceleration of A is also known to us. Okay, I'll just bring the velocity expression as well from above here. Okay, so I'm going to copy that and I'm going to bring that down here. All right, so we know these two. These are the absolute velocity and acceleration of point A. All right, now we are ready to analyze the bar BC. Okay, so let me do that. I don't need this. Let me put a different color here so that it makes sense. Now we shall analyze the bar BC. Okay, but before I do that, I need to do one thing. Okay, I need to find the angle made by the bar BC with the horizontal. So look at this very quickly. If I go back to my figure here, okay, I'm going to join the point B and the point O, and I'm going to assume that they are on the same straight line. So I'm going to take points B, A, and O. Okay, maybe I should capture my figure and then bring it so that we can see it. Okay, so let me do that here. I'm not sure if I'll have space for it. All right, I do have space for it here. Well, let me just bring it to the next page. Apologies. All right, so here what I'm going to do is I'm going to draw the points O, B, and A, and I'm told that B and O are on the same line, so I'm just going to draw them together this way. Okay, so here is the point B, here is the point O, and then I'm just going to draw the point A. Okay, so this is the point A, and join them together. I know this distance is 0.2 meters. Distance from O to B is given to me as 0.6 meters. and I know that this angle here is 60 degrees. So even though the distance from A to B is given to me, okay, which I'll call as L, and I'll call this angle as some theta. If this distance L was not given to me, then I can still find L by using the cosine rule. Okay, so I can find L square is equal to 0.2 square, 0.6 square minus 2 times 0.2 times 0.6 times cosine of 60 degrees. Okay, so if I do the square root, L is approximately 0.53 meters, which is what is given to me. Okay, so this is can be obtained by making use of the cosine rule. The angle theta can be obtained by making use of the sine rule. Okay, so that's going to be the following. So L by sine 60 is equal to 0.2 by sine theta. Now, why am I looking at the angle theta? That's an important question, right? I'm looking at the angle theta because I need to know, since the bar BC is a rotating body, I need to set up a new pair of rotating axes on this body. And so I need to know what the angle of that axis is with respect to the horizontal at that instant in time. So this is the reason I'm trying to find the angle theta. Okay, so find the angle theta from here, solve for theta. Okay, and then you'll end up getting theta is approximately, have the answer somewhere here, around 19.1 degrees. Okay, so we are able to find both the length and the angle theta of 19.1 degrees. So even though we were given the length here as 0.53, I can still find it if necessary. Okay. All right, now we are ready to draw the bar BC, and I'm going to grab hopefully just the bar BC. Let's see if that works out. So I'm going to copy all of, okay, I kind of lost that there. I'm going to copy, I don't need the disk. I think I caught the disk as well, but let's see. I can always get rid of the disk. I'll get rid of the disk, and then I missed out on some parts of this link. So I'm going to copy that and bring that down here, close the lid here. And then I have this one situated. This is on a fixed surface. Okay, so that's the bar BC, and then the peg at A. Okay, I'm going to grab that peg as well. So I'm going to copy that, and I'm going to paste that and bring that guy down there. All right, so beautiful. This is how the situation is set up. Okay, and the length is 0.53. The angle made with respect to the horizontal is known to me now. So if I just draw a smooth straight line here, let me draw it as a dotted line. Okay, then I know the angle made with respect to the horizontal for that particular line. Okay, that angle is given to me as the angle theta, which we found out to be 19.1 degrees. Okay, that was in the previous page or previous calculations. All right, now comes the question of setting up coordinate frames. Okay, what kind of a coordinate frame should I set up? Now I know that the point A is not a part of the link BC, so that's something I want to note here. So note that point A is not a part of BC. Okay, which implies that the distance from A to B is not fixed. Is not fixed. All right, so I'm going to set up a new pair of coordinates or unit vectors here. So I'm going to call this unit vector here as the unit vector, let's say E1. Okay, then I'm going to have another one that is perpendicular to it, which I'm going to call as the unit vector E2. The reason why I'm taking E2 to be this way is so that if I cross my fingers, if I do the right hand rule going from E1 swinging all the way to E2, my thumb comes out of the page, and that's going to be called as E3. Okay, so E3 is coming out of the page in this situation, which is going to be the same as the K. Okay, so this is my coordinate frame, and I also obviously know that this here, which is hopefully a straight line, right? That's going to be the I direction and then the J direction. So I can pin the I and the J directions along with that. So if necessary, I can write this as the I direction, okay, and then I have the J direction written down here. Okay, that's the inertial frame. So let me write down a few things. Okay, so the unit vector system E1, E2, and E3. This is a rotating triad and rotates at the same rate as the bar BC. Okay, the unit vector ijk is a fixed frame. As you know. Okay, and I have the angle between the two of them there. All right, so with that said, I'm going to grab this figure once again. Okay, so I'm going to copy this, and I just want to make sure that this distance here is aligned with the E2 direction. So just to make everything clear, okay, this distance has to be aligned with the E2 direction. So my E2 is supposed to be taken along the distance that I'm measuring it from with respect to the point B. Okay, all right, so that's the distance of 0.53 given to us. All right, okay, so I'm going to grab this picture and start looking at how to solve this. Now we first do velocity analysis, as you know. Okay, so let's see. Excuse me. I have the velocity of A, which is already known to me. Okay, so velocity of A, which is known to me, is given by 7.4 I and then 2 in the J direction. This is so many meters per second. Then I say, okay, hey, what is the distance from point A to point B? This distance is along the E1 direction, right? So R from sitting at the point B, looking at the point A, I know that that distance is going to be 0.53 in the E1 direction. Okay, what's the direction of the relative velocity? Since A is not a part of B, I'm going to have V A slash B relative, and this relative velocity is an unknown relative velocity, so I don't know the magnitude of this particular term, but I do know its direction. It's going to be along the E1 direction, right? Because this essentially is obtained by fixing the bar BC and looking at how the point A slides relative to the point B. Okay, so that's another thing that I know. Then do I know anything about the acceleration, the relative acceleration? I can say that this is also along the E1 direction using the same argument I had for A slash B. Now I don't know the omega and alpha of the bar BC, so I'm just going to assume it to be counterclockwise. Okay, so omega of the bar and alpha of the bar. Okay, so this is omega BC, this is alpha BC, so I'm going to assume that omega BC is omega BCK and alpha BC is alpha BC the K direction. All right, and I know that the velocity of B is 0 because it's a fixed point. Okay, the acceleration of B is also 0 because B is a fixed point. All right, so now I'm ready to write my equations. Let me start off with the velocity analysis. Okay, so here is where I make use of the entire set of equations that I have for velocity analysis. So I'm going to say velocity of A is velocity of B, omega of the bar BC crossed with A slash B. And then I'm going to have the relative velocity, which in this case is not 0. Okay, as you can very well see. I'm going to substitute velocity of B is 0, of course, because it's a fixed point, right? So I'm going to substitute for velocity of A, which is 7.46 I and 2J, okay? And this is going to be omega BC, which is omega BC K, crossed with R A slash B, which is going to be 0.53 in the E1 direction. And then I'm going to have VAB relative multiplied by E1. I have my triad Okay, my triad is, I can write that down here. So E1, E2, E3. Okay, so here is my triad. And if I do E1 crossed with E2, it gives me E3. That's essentially what it says. Okay, so in here, and E3 is the same as K, as you know. Okay, so in this case I have K cross E1, which means that I'm going to get the E2 direction, right? So K cross E1 gives me E2. So I'm going to have the following: 7.46i and 2j. This is equal to VAB relative in the E1, and then 0.53 omega BC in the E2 direction. Alright, now we come to a crucial point in our calculations. We need to perform the coordinate transformations. So how do we do the coordinate transformations? So coordinate transformation, because these are in a mixed system, right? On one side I have I and j, the other side I have E1, E2, so obviously this is not going to be helpful to my life. So I have to do a coordinate transformation. Now, do I go from E1, E2 to I and j, or do I go from ij to E1 and E2? The obvious answer is should be I go from I and j to E1 and E2, because then I can just compare the terms on both sides to obtain my unknowns. Okay, if I do the transformation from E1 and E2 to I and j, then I'm going to have terms containing I and j on the right hand side, terms containing unknown quantities in the I and the j directions, both on the left hand and right hand side. So I'm going to have to solve a system of equations, which is not very efficient. Okay, so in this case it is more efficient to do the transformation from I and j to E1 and E2. Okay, so in this case we're going to do the coordinate transformation I and j to E1 and E2. Okay, then let me do this transformation very quickly. So I'm just going to set up my E1 and E2 unit vectors here. So this is E1 and this was E2, of course perpendicular. This was E1, and let me grab this figure once again and write it down here. Okay, so that I can do the j direction here and the I direction here. So this is the I direction, and I'm just going to extend that here until here. Okay, so this is I, and this angle here is theta, and then here is my j direction. Okay, and I can very well quickly see this. Go back to the figure. If this angle here is theta, then this angle here is also theta. Okay, because I and j are 90 minus theta. Okay, alright, so this angle is also going to be theta here. So this is going to be my j unit vector. Immediately for the I unit vector, I recognize that, okay, I need to bring E2 onto the other side. Okay, so that's exactly what I do. Okay, so I grab this E2, bring it onto the other side here, so that I extend it down here. Alright, and then from the head of I drop perpendiculars down onto the E1 and the negative E2 directions. Okay, so this is perpendicular, this is perpendicular, that's good enough for me there. Okay, then this is the negative E2 direction, as you know. Okay, and so what are the distances I have here is cosine theta, and then I have sine theta. And likewise I can do the same thing for the j direction. From the head of j I drop a perpendicular onto E2 positive, and then E1 positive. Okay, these are all supposed to be perpendiculars, and then I can say that, okay, hey, this guy is cosine theta and that is sine theta. Okay, so which means I can now say that I is cosine theta E1 minus sine theta E2, and then j is going to be the following. Okay, it's going to be sine theta E1 plus cosine theta E2, and theta is 19.1 degrees, right? That is from before. All right, then I go ahead and grab my velocity expression from here. Okay, with the coordinate transformation done, I go ahead and grab it and bring it down here, okay, and then I start doing the substitutions. Okay, so this is 7.46 in the I direction, which is cosine of 19.1 E1, sine of 19.1 E2, plus 2 times the J direction, which is sine of 19.1 E1, cosine of 19.1 E2. Okay, this is equal to stuff on the right hand side, which is VA slash B relative in the E1, 0.53 omega BC in the E2 direction. Okay, then I take vectors in the E1 direction, vectors in the E2 direction, or components in the E1 and E2 directions, and equate them to each other. So this is 7.46 cosine 19.1, okay, plus 2 times sine of 19.1 is VA slash B relative, as you can very well see, okay, and then I'm going to have minus 7.46 sine 19.1 plus 2 times cosine 19.1. This is equal to 0.53 omega BC, as you can see here. Okay, and I just start plugging in the values and so on. So there is not much more to this, as you can see. Okay, VAB relative, I can solve for VAB relative, which is going to give me approximately 7.7 meters per second. This is the velocity of A relative to B. Okay, and then I can also solve for omega BC, which I end up getting as a negative number here. Okay, it's minus 1.01, minus 1.1 radians per second. This is the angular velocity of the bar BC. Alright, this is fantastic. All I need to do is do the accelerations and then call it a day. Okay, so let's do that quickly. Alright, so look at the accelerations now. Okay, so previous case we did the velocity. Let's do the accelerations. I'm going to grab some information from here. Okay, so I'm going to grab all of these guys and I'm going to change a few things, of course, from there. I'm going to copy that first, bring it down here. Okay, now VAB relative, we found out what the value is, so I can start filling in the details of that. So this is going to be 7.7 E1, so many meters per second. A relative, I don't know yet. Omega BC, I found out to be in the negative K direction, right? So this means that I can get rid of that and say this is now minus 1.1 K, so many radians per second. And the assumption is now going to be only for alpha BC. VB and AB are still 0. This position vector is still the same as it is. Then I can go ahead and grab the acceleration of A, which we had solved for earlier, right? That is from here. Excuse me. Alright, that's the acceleration of A, which I had solved for from earlier. Bring it down here. Alright, so we have all the ingredients needed for our good soup. So let's write this down. Acceleration of A is acceleration of B, then alpha of BC crossed with R A slash B, omega square BC times R A slash B, plus A slash B relative, which is not 0 anymore, and then this term 2 omega of BC, I'm sorry, crossed with V A slash B relative. Among these, only acceleration of B is gone. Excuse me. Start substituting. Okay, so I'm going to have the following: 38.1 I minus 70.2 J. Okay, this is equal to, let's start a big bracket here, alpha BC, which I assume to be in the K direction, crossed with 0.53 E1, that's one term. Then omega square BC is 1.1 square times 0.53 E1. Then a slash b relative, I'm just going to grab it and write it as a slash b relative in the E1 direction, which is what I have here. I have, I guess I don't need to cut it. I have assumed it to be this way as positive E1. I don't know if it is positive or negative E1. Okay, I'm just assuming it this way. And then 2 omega bc, so be careful here. So this is now going to be 2 times minus 1.1 k crossed with 7.7 E1. Okay, that is the last term there. Then start doing the substitutions. Okay, so let's bring it to a nice form. So this is 38.1i, 70.2j. Okay, this is equal to the following. Collect all the E1, E2 terms. Okay, now I have a slash b relative E1 and 0.53 in the E1 direction. Okay, so collect all those terms. So this is going to be a slash b relative minus 1.1 square times 0.53. This is all in the E1 direction. How about the E2 direction? K cross E1 is E2, right? We had the triad here. Okay, so if you want, you can bring this triad once again down here and then look at it. So copy that and then bring it down here. So you can write it down here. K cross E1 is E2. So I need to bring it a little up here. Okay, so this is the triad which is situated here. So I'm going to have 0.53 alpha BC. And then I'm going to have 2 times minus 1.1 is minus 2.2. K cross E1 is E2. So this is going to be minus 7.7 times 2.2 in the E2 direction. Okay, so all of them put together E2. And same idea, instead of I and j, I have to do the substitutions from the coordinate transformation, which we already have from here. Let me just go and grab that thing. Okay, so here is what I had for the coordinate transformation. Copy that and bring it down here. Okay, then start doing all the substitutions. This is just going to be a huge mess, as you know. Right, so this is cosine 19.1 E1 minus sine 19.1 E2 minus 70.2 times sine 19.1 E1 cosine 19.1 E2. Okay, and that's all the terms there. This is equal to a huge host of terms here, a slash b relative minus 1.1 square times 0.53 E1, and then I'm going to grab that other term from here. Okay, copy that and paste that down here. That's the term in the E2 direction. And exactly the same idea as before. Look at the terms in the E1 direction. 38.1 cosine 19.1. Okay, then minus 70.2 sine 19.1. This is on the left hand side. On the right hand side, this is a slash b relative 1.1 square times 0.53. Look at the E2 terms. This is going to be minus 38.1 sine 19.1 minus 70.2 cosine 19.1. This is equal to 0.53 alpha BC minus 2.2 times 7.7. And all we are left to do is solve for alpha BC and a relative and so on. So if I do the calculations, I end up getting the following. Okay, so from here I can solve for a slash b relative, and I obtain this to be around 13.3 meters per second square. Okay, and then likewise I can solve for alpha. This is the relative acceleration of a relative to b. Okay, so let me just say that, cut this off. This is acceleration of a relative to b, or relative to the link BC. It doesn't matter, it's the same thing. Okay, because a is not a part of the bar BC. And then I'm going to have alpha BC, which I end up getting as minus 116.7 radians per second square, so that the vector alpha BC is minus 116.7 k radians per second square. This is at that instant in time. Okay, this is the angular acceleration of the link or the bar BC. Alright, so this is a really good problem. Exercises a lot of aspects of relative motion and also coordinate transformation. Okay, so very quick recap of the problem. Just going to go ahead and look at the first picture here. I'm given a disk rolling without slip. There is a peg embedded on the disk. There is this link BC which is attached to the point B on a fixed surface. The point A can slide relative to the link BC. I need to find, given the acceleration and velocity of the disk, the angular velocity and acceleration of the disk, and given the fact that it rolls without slip, obtain the angular velocity and acceleration of the bar BC. So my first strategy is to look at only the disk, obtain the absolute velocity of A and absolute acceleration of A, using the idea of rolling without slip. That's all that we have done here. Okay, I obtained velocity of A, then the acceleration of A. Then after analyzing the disk, we now analyze the bar BC. For the bar BC, I need to do some geometry, cosine rule, sine rule. Okay. In fact, the distance 0.53 was given to us, but we still calculated it anyways. Then I make use of the fact that A is not a part of the bar BC, which means that I have to set up a new pair of coordinate frames, E1 and E2, which will track the motion of the point A relative to the bar BC. This is at an angle of 19.1 degrees with respect to the I direction. So that's necessary for us to know. Okay, then I just bring in all the equations of relative motion. I have to perform a coordinate transformation, and this is something that you have done when we looked at particle kinematics a long time back. And once you do the coordinate transformation, then you're ready to solve for the unknowns, and the exact replica of this is done in the acceleration analysis with an extra set of terms. Once again, coordinate transformation results are necessary for us. Substitute that and then solve for the unknowns. Okay. All right. This was a nice problem. A lot of work involved in this problem. So you want to think of how to maximize or how to be most efficient when you're solving these kinds of problems. I hope all of you are staying safe. Take care of yourselves, and I wish you a great day. Bye-bye.